A very good example of a combination of a translational and rotational motion is a rolling ring. If we look at the path traced by a point on the circumference of a ring, then its motion seems to be quite complicated. However, the center of mass of the ring can be seen to be moving in a straight line. If we switch our frame of reference to the center of mass of the ring, then the ball appears to be having only a rotational motion. Let us attach a ring to a movable rod at its center of mass, and then give it a rotational motion. Now, if we move the rod like this, the motion of the ring is similar to the ring rolling on the ground. That is to say, that the rolling motion of a ring can be split into a pure translational motion and a pure rotational motion about its center of mass. This is effectively similar to resolving a vector into components. So the motion of any point on the ring will be the vector sum of the translational motion and the rotational motion. If the linear velocity of the center of mass of the ring is equal to v, and its angular velocity about its center of mass is equal to omega, then we can say that the velocity of this point at this moment will be equal to v plus omega r. Similarly, velocity of this point will be equal to v minus omega r. An interesting point from this equation is that if the linear and the angular velocity of a rolling object is such that v is equal to omega r, then the instantaneous velocity of this point will be equal to 0. That is, the point in contact with the surface is momentarily at rest. In fact, if we look at the motion of a rolling ring, we can say that the distance moved by center of mass will be equal to this length of its circumference, which can be written in terms of angle theta as r into theta. Differentiating this equation with respect to time, we can say that the velocity of center of mass will be equal to r into the angular velocity of object, which is in fact the case. Such a rolling is also known as pure rolling. We can infer the same by saying that as the object is not slipping over the surface like this or like this, then the relative velocity of this point with respect to the ground should be equal to 0. But doesn't it seem strange? How can a moving object be stationary at the point of contact? Actually, such a motion is very common in our everyday life. If we see someone walking, then overall, the person is moving, but his point of contact is stationary. Though, after a while, his point of contact will change. But till the time his foot is in contact with the ground, it is at rest. Let us consider a situation that is closer to the case of rolling. If we consider such a motion of this object, then though the object is moving forward, but its point of contact does not move, after a while, the point of contact is a different point. But still, as long as it is the point of contact, its velocity relative to ground is 0. Now, if we increase the number of sides of our object, then the point of contact will change more frequently. But the instantaneous velocity of the point of contact remains 0. Increasing the number of sides to an extent that it becomes a round object, we can say that though its point of contact will change every instant, But just for the moment, that point is in contact with the ground. Its instantaneous velocity is 0. Here you must note that this argument has arrived from the fact that the relative velocity of the point of contact with respect to the surface over which it rolls is 0. So we can say that if the object rolls without slipping over a moving surface, then the instantaneous velocity of the point of contact is equal to the velocity of the surface